Okay, we just restarted. Let me try to see if this worked. Great. Now we lost information. How is this not UTF? Man. Why did it let me save and not give me an error? Because I saved it before I exited and it was like, cool, man, you did it. Good job, you saved. Nada. Broken. Really broken. Still broken, I should say. Check that out though. Let's check the properties. It's in UTF-8, the current code page. And the font is Lucidia console, which is a UTF-8. Why? Why is the support for these things so horrible? Why isn't this as an option? Why doesn't it work? Where's my window? Nada. No character was printed. It's not printing. Why not printing? Will print anything else? It's working with as. Why? We have the code page. We have the font, which is compatible with the code page. We have the data type that can store the character. It's obviously displaying it and working properly in Visual Studio. The values correspond correctly to the values in the character. But I mean, we're getting no output. If it works in here, why not over there? We're using the same code page. Not the same. Not the same font. Let's give this a go. Nada, nothing. It's broken. Why? It makes no sense. It makes no sense. We're using Consoles font. We're using the same code page. We're using the same character. It's just no work. Just doesn't want to do it, huh? It just doesn't want to do it. What the hell is this? Raster fonts. I don't think this is... Even this one is using the correct one. Well, at least we got it to do this. This is the IBM. I guess it's displaying the current code page to be that, but it's not actually using that code page. Okay. I think we got the saving fixed, but not this. Let's see if we actually fixed the saving. Let's see if we made any progress. Woo! We made progress. It knows what that is. Okay, so is the code working? Let's see if that's working. Well, I had a breakpoint in it, so I think it probably would break. Not that I think it worked. Huh? It's not working at all now? What's happening? Where are we? Line 16. No, that's the process number. Where are we? Let me pause it. Yeah, where are we? We're CN, we're waiting. I guess if it just hits this character, it just breaks utterly. Yep. So it does break. Okay. Please tell me this is available. Broken. 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 Broken, 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 broken. I think we're getting closer. Where is set mode defined in? We just need to get that. Where is it? Alphabetical function reference. C runtime. Well, where is that? This might work. Getting farther. No results. How's the IntelliSense know where it is? Not complain about it, but these don't. That doesn't make any sense. We got 3 errors, but no errors down here. Where are these errors? What? Everything's just broken. Screw it. Build it. Anyways. It broke. Everything's broken. Everything's broken. System independent approach. I like the words of that. Please, please, please tell me this works. I need this to work. It's okay. Might fail. Depreciated. What? Okay, so you depreciate it, and then the C++ standard doesn't provide an equivalent non-depreciated functionality. So I can suppress the warning? Will it break things? This works, I'm gonna be mad. Okay, well it didn't work, that's okay. Okay, so it looks like there's a problem with wcout narrowing our wide characters back to characters before writing them to the buffer, where then the operating system runs with console. How do I get it to work? Okay, looks like we do have to talk to the Windows operating system to get this working. That's okay, we're gonna be working with the Win32 system eventually anyways. Now, these are undefined. We're gonna try this. Hallelujah, we're getting somewhere, baby. Well, at least it didn't explode and stop outputting any characters. Still not working though. Broke. So this is helping. Let's see why it's not working. Don't think we need this. Yeah, I don't think we needed that. That's file buffering. We need line buffering. Oh. No, that'll work. Oh, full buffering. Oh, this is fun. This is how I want to spend my weekend. Okay, hold on. Let's take a step back. And try to figure this out the hard way. Well, the book's not helping me anymore. Yep. I'm gonna go to the big guns. I still want to be a little zoomed in. Don't like this, but we're gonna do it. Introduction to Unicode, page 19. Okay. Unicode is an extension to the ASCII character encoding rather than 7 bits in a strict ASCII, or the 8 bits per character has become common. Full 16 bits. 16, not even 8. That's good. And we're moving to... Come on, autofocus, do something appropriate. The double byte character sets, Unicode rescue. Let's get to the functions. Wide characters, WCHART. And let's set the focus. Okay. Okay, so we got the wider characters. We are using those. Wide character functions. And then using the text macro and tchars. Understand that. We have the Windows message box, which might be our solution to this. Printf. Formatting message box. Well, we can. I think we can get it working with the message box W function, but that changes the output from a console type program to a Windows subsystem program. Let's get this. Give it an attempt. Message box. That works. I don't even need message box W. I mean, this works. Okay. Weird formatted message box we did. We programmed. I'm gonna use that. We need these things as well. Oops. This isn't even solving the problem. It's just moving it to a different place where it does work. Okay. Alright, we're gonna give up on this. Go with the lazy approach. Utterly lazy approach. Let's just call this a yen. What's a sterling called? We're gonna use abbreviations instead of, you know. GBP. UK. L. GBP. GBP. What is the yen abbreviation? JPY. JPY. Apparently there's a codes. Currency code. $0.16. Does that make sense? I don't think so. That really doesn't make sense. That's a kroner. Yep, okay. Give that a go. 1,000 yen. $6.07. Does that make sense? 1, 2, 3. Yes, it does. I guess. KR, that's not what we want. Nope. Okay, well that's the longest try this we've experienced so far. Thank you for the C and C++ runtime libraries not supporting Unicode, data transfer or whatnot. Apparent lack of support for Unicode input output in Microsoft C and C++ runtime libraries. Particularly problematic. Yep. It's funny that that's a problem. And yet I can get a message box to pop up with Unicode, which is like even a more complicated thing. And it works. Okay. Let's bring the book back in. Let's continue on. reasonably in focus. Not sure why it is. I would not have expected it to stay in focus. We changed it to a different height. That's okay. I'll take a win when we can. Okay, so we got switch statements. Actually, the comparison of unit of I and to C is an example of one of the most common forms of selection. A selection based on comparison of a value against several constants. Such selection is so common that C++ provides a special statement for it, the switch statement. We can rewrite the selection part of our unit example as we switch on some unit and we provide 3 cases, one for an I, one for a C, and one for a default, which is neither I or C, and we perform some functions based on what cases we ended up getting on. We have an advice alert marker here. The switch statement syntax is archaic, but still clearer than nested if statements, especially when we compare against many constants. The value presented in parentheses after the switch is compared to a set of constants. Each constant is presented as part of a case label. If the value equals the constant in a case label, the statement for that case is chosen. Each case is terminated by a break. If the value doesn't match any of the case labels, the statement identified by the default label is chosen. You don't have to provide a default, but it is a good idea to do so unless you are absolutely certain that you have listed every alternative. If you don't already know, programming will teach you that it's hard to be absolutely certain and right about anything. Here are the switch technicalities. Here are some technical details about switch statements. 1. The value on which we switch must be of an integer, char, or enumeration type. In particular, you cannot switch on a string or a floating point value. 2. The values in the case labels must be constant expressions. In particular, you cannot use a variable in a case label. 3. You cannot use the same value for 2 case labels. 4. You can use several case labels for a single case. 5. Don't forget to end each case with a break. Unfortunately, the compiler probably won't warn you if you forget. Now, it doesn't explain here, but the reason why we break, or I guess we're going to learn down here why it breaks, is because it falls through. So without this break, you switch, you go to the case no, and if you didn't have that break, you would continue down and process them. Okay, so the focus is bad. So let's configure that. Okie dokie. For example, you can get switch only on integers, etc. So we have cout, do you like fish? We have a string, s. We input our answer into s. We attempt to switch on s, but we have an error. The value must be of integer, char, or enumeration type. So it's break. To select based on a string, you have to use an if statement or map. See chapter 19. A switch statement generates optimized code for comparing against a set of constants. For larger sets of constants, this typically yields more efficient code than a collection of if statements. However, this means that the case label values must be distinct and constants. For example, int y equals the character y. This is going to cause trouble. Const car n equals the character n. Cout, do you like fish? We grab a character for an answer, and then we switch on this character. In a case n, for no, I guess, we do some working, and if it's the case yes, I see the problem. Y, error, the variable in the case label. Okay, so int y is a variable, not a constant. If we did a const expression at int y or a const int y, it would probably work. But we didn't do const. We need const there. Case n, error, duplicate case. N's value is in n, so despite n here being a constant expression char, and the character n, because they have the same value, n and the character n, we get a duplicate error. Often you want the same action for a set of values in a switch. It would be tedious to repeat the action, so you can label a single action by a set of case labels. For example, you can label a statement with several case labels. We have cout, please enter a digit. Car A equals 0, and we grab a car from the person. We switch on that character that we got, and we have several cases, one after another. This is interesting. So often you run the same action for a set of values. Okay, so we can put them all here as even, and we can put them all here as odd, and default is not a digit. Okay, that's pretty good. Seems pretty useful. I like switch statements. I didn't know you could do that. I would have put them all vertically and then put it. Okay, so we have a warning alert marker here. The most common error with switch statements is to forget to terminate a case with a break. For example, we switch on a unit, and it looks like we have our case I, and we print out then we have a case C, but there's no breaks. Unfortunately, the compiler will accept this, and when you have finished the case I, you will just fall through into case C, so that if you enter 2i, the program will out 2 inches equals 5.8 centimeters, and also 2 centimeters equals 0.787402 inches. You have been warned. In the rare case where you want to fall through to the next case, you can and should say so. Fall through. Okay. What is that? Fall through is an attribute making our intent explicit. What is it though? Okay. All right. We have a new try this. Rewrite your currency converter program from the previous try this to use a switch statement. Add a conversion from Swiss francs. Which version of the program is easier to write, understand, and modify, and why? Okay, let's do that. I'm done. It's getting too hot in here. I'm going to turn on the air conditioner. It's gonna get noisy. Obviously, I usually record with it turned off, but over time, the room just naturally heats up with me and the computer being in it. Okay, let's try this. Well, before we leave this project, we want to copy it. I'll copy the main CPP because we're going to be reusing a lot of code from it. And create a new project. New empty project. PPP free. Try this. Currency. Converter. Switch. And then we're going to open our folder in the view. We're going to paste a file. And close this. We can add an existing item, the file we just pasted over. And then edit the project properties. C++ language standard. And build ISO C++ standard library to yes. Apply these changes. Yen, kroner, pounds, or francs. Swiss francs. Is that right? We want us to do Swiss francs? Yes. Yes, it does. Okay. Switch. I'm going to switch on the currency selection. In case Y. Case K. Case P, and we want a case franc, I guess F. What is the Swiss franc? Oh, that's feeling better already. Franc code CHF. Case default. Don't need the break. Get rid of that. GB CHF. Might as well make this more equivalent. And we need to know the conversion rate, or at least the current conversion rate. bad. 1.25. Let's give this a go. 100 yen. Correct. $1K. Correct. 1P. Correct. 1F. Interesting. Oh, it fell through. Oopsie daisy. I was warned, and I did it anyways. Let's see if we fixed it. 1F. That works. And let's give it something else. 1Z. So I don't know what currency is related to Z. See options above. That's okay. And this is good. Okay. That's it. That's all that try this took. Simple requests get done quickly. No properties. Get the camera control. Come on. Back in focus. Alright, section 4, subsection 2, iteration. We rarely do something only once. Therefore, programming languages provide convenient ways of doing something several times. Doing the same thing to a series of objects is called iteration. And the while statements. As an example of iteration, consider the first program ever to run on a stored program computer, the EDSAC. EDSAC. It was written and run by David J. Wheeler in a computer laboratory in Cambridge University, England on May 6, 1949, to calculate and print a simple list of squares like this. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared, 9, 4 squared, 16, all the way up to 99. Each line is a number followed by a tab character followed by the square of the number. A C++ version looks like this. We have a small program here, in which case int I equals 0, start from 0, and while I is less than 100, we print out I with a tab, and then the square of I, and a new line, and then we increment up I, and we start the loop back up again. The notation square I simply means the square of I. Later we will explain how to get it to mean that. No, the first modern program wasn't actually written in C++, but the logic was as is shown. We start with 0, we see if we reached 100, and if so, we are finished. Otherwise, we print out the number and its square separated by the tab, increasing the number, and try again. Clearly, to do this, we need a way to repeat some statement to loop, and a variable to keep track of how many times we have been through the loop. A loop variable, or a control variable. Here, the int called I. an initializer for the loop variable here 0, a termination criterion here. Okay, it's a continuation of here. So way to repeat. So we need a way to loop, and we need a loop variable, a control variable. I lost where I was in my mind. We need an initializer for the loop variable. Here we have 0. Termination criterion. Here we want to go through the loop 100 times. And then something to do each time around the loop, the body of the loop. The language construct we used is called a while statement. Just following its distinguished keyword while, it has a condition on top, followed by its body. While I is less than 100, the loop condition testing the loop variable I. We have the body. We have the increment of the loop variable. The loop body is a block delimited by curly braces, shown here. That writes out a row of the table and increments the loop variable I. So that's what's happening here and here. We start each pass through the loop by testing if I is less than 100, here. If so, we are not yet finished, and we can execute the loop body. If we have reached the end, that is, if I is 100, we leave the while statement and execute what comes next. And we leave the while and do what follows. In this program, the end of the program is next, so we leave the program. The loop variable for a while statement must be defined and initialized outside before the while statement. If we fail to define it, the compiler will give us an error. If we define it but fail to initialize it, most compilers would warn us, saying something like local variable I not set, but would be willing to let us execute the program if we insisted. Don't insist. Compilers are almost certainly right when they warn about uninitialized variables. Uninitialized variables are a common source of errors. In this case, we wrote int I equals 0, start from 0. So all is well. Basically, writing a loop is simple. Getting it right for real-world problems can be tricky, though. In particular, it can be hard to express the condition correctly and to initialize all variables so that the loop starts correctly. So let's try this. The character B is car A plus 1, C is car A plus 2, etc. Use a loop to write out a table of characters with their corresponding integer values. Okay? A table of characters. Alright, let's stop at Z. Alright then, let's get that done. File, new project, empty C++ project, keyboard time. PPP3 underscore try this, and this will be loop. Add our main CPP, project, properties, general, scan sources for module dependencies, the yes, language, standard to latest, and build the standard library to yes, apply. This program iterates over the alphabet and prints its numerical equivalence. So let's import std using namespace std int main. Right, for we have the character C equals A, and while C is less than z plus 1. We want to cout c as well as we have well, let's just convert it to an int c. I haven't explained conversions yet, so we won't use them. Run this, give it a go. Alright, appears that worked. Okay. Alright. Keep losing my pointer in the crease of the book. Alright. Well, we finished this try this, so let's go to blocks. Note that we grouped the two statements that the while had to execute. A sequence of statements delimited by curly braces is called a block statement, or a compound statement. A block is a kind of statement. The empty block is sometimes useful for expressing that nothing is to be done. For example, do nothing. For statements. Iterating over a sequence of numbers is so common that C++, like most other programming languages, has a special syntax for it. The for statement is like a while statement, except that the management of the control variable is concentrated at the top where it is easy to see and understand. We could have written the first program like this. Int main, and we have for I equals 0, semicolon, I is less than 100, semicolon, and then plus plus I, with our body, the printout of I, separated by a tab, and its square of I. This means execute the body with I, starting at 0, incrementing I after each execution of the body until we reach 100. A for statement is always equivalent to some while statement. In this case, for int I equals 0, I is less than 100, plus plus I, cout I, the tab and square of I, a new line character, is equivalent or means while int I equals 0, while I is less than 100, cout, print out I, separated by a tab and its square and a new line character, and increment up I. So this top section, we have the for statement initializer. This while I is less than 100 is equivalent to the for statement condition here. The for statement body here and here are equivalent. And then the for statement increment here and here are equivalent. Some novices prefer while statements, and some novices prefer for statements. However, using a for statement yields more easily understood and more maintainable code whenever a loop can be defined as a for statement with a simple initializer, condition, and increment operation. Use a while statement only when that's not the case. Never modify the loop variable inside the body of a for statement. That would violate every reader's reasonable assumption about what a loop is doing. Consider. Bad code. For int I equals 0, I is less than 100, I plus plus. For I in the range of 0 to 100 range. We have cout I, print out I separated by a tab and it's square with a new line character. And then we have plus plus I within the body of this for function. Alright, what's going on here? It smells like an error. Anyone looking at this loop would reasonably assume that the body would be executed 100 times. However, it isn't. The I++ in the body ensures that I is incremented twice each time around the loop, so that we get an output for only 50 even values of I. If we saw such code, we would assume it would be an error, probably caused by a sloppy conversion from a while statement. If you want to increment by 2, say so. Calculate and print a table of squares of even numbers in the 0 to 100 range. So here's how we could do that. So for int I equals 0, I is less than 100, I plus equals 2. With cout, and we print out I separated by a tab and it's square and a new line character. Alright, advice. Please note that the cleaner, more explicit version is shorter than the messier one. That's typical. I guess it's more cleaner and explicit is more typical to be short. Try this. Rewrite the character value example from the previous try this to use a for statement. Then modify your program to also write out a table of the integer values for uppercase letters and digits. There is also a simpler range for loop for traversing collections of data, such as vectors. See section 6 coming up. We're going to get there. Alright, so let's try this. So, before we make a new program, we want to copy main CPP because we're going to be reusing a bunch of the code. File, new project. Empty C++ project, PPP3, try this. For loop. And open folder in File Explorer, drop in the main CPP, add it as an existing item, edit. Project properties, scan for source, scan for module dependencies, change the language standard to latest, and build the ISO C++ standard library up, apply, open up main, case and case. Alright. So, okay, for C, A, C is less than that. Plus C. That's it. And then we want to do uppercase A, Z. Alright, let's try that. Oh, we're going to double initialize. Wait, it let me do it? I'm surprised. It let me double initialize. That doesn't make sense. Look. We did it several times, actually. It let us redefine it? Oh, no, it's separate C's. That's interesting. Whoops. That seems a little better to me. I don't like the lack of curly braces. I don't like it. It's a personal preference of mine. See, now we only have one C. There we go. Ah, I forgot. Huh. Oh yeah, I forgot the uppercases come first in the ASCII character set. Okay. That finishes that one. Alright. We have Section 5 of Chapter 3, Functions. In the program above, what is square of I? It is a call of a function. In particular, it is a call of the function called square with the argument I. A function is a named sequence of statements. A function can return a result, also called a return value. The standard library provides a lot of useful functions, such as the square root function, sqrt, that we used in Section 4 of Chapter 2. However, we write many functions ourselves. Here is a plausible definition of square. Int square, taking the input parameter int x with the argument, and we return x times x. The first line of this definition tells us that this is a function. That's what the parentheses mean. That is called square. That it takes an int argument, here called x, and it returns an int. The type of the result comes first in a function declaration. That is, we can use it like this. Cout square of 2, and we output space and the square of 10. And we print out, it prints 4 and 10. We don't have to use the result of a function call, but we do have to give a function exactly the arguments it requires. Consider. Square of 2. Probably a mistake, an unused return value. So square of 2 returns 4, but it's not being used, so it doesn't go anywhere. We have int v1 equals square of nothing, which will give us an error because it's missing an argument. We have int v2 equals square, which is an error, we're missing parentheses. We have int v3 equals square 1 and 2, an error, we have too many arguments. And int v4 equals square of 2, the literal string 2. And an error, the wrong type of argument, it was expecting an integer. Then we have a core concept alert marker. Many compilers warn against unused results, and all give errors as indicated. You might think that a computer should be smart enough to figure out that by string 2, you really meant the integer 2. However, a C++ compiler deliberately isn't that smart. It is the compiler's job to do exactly what you tell it to do after verifying that your code is well formed according to the definition of C++. If the compiler guessed about what you meant, it would occasionally guess wrong, and you, or the users of a program, would be quite annoyed. You'll find it hard enough to predict what your code will do without having the compiler help by second-guessing you. And we have the function body is the block. That actually does the work. For square, the work is trivial. We produce the square of the argument and return that as our result. Saying that in C++ is easier than saying it in English. That's typically for simple ideas, after all. A programming language is designed to state each simple idea as simply and precisely. The syntax of a function definition can be described like this. Function definition, colon, type identifier. Okay, sorry. We have the type identifier, the function identifier, a parameter list, and then a function body. That is, a type, the return type, followed by an identifier, the name of a function, which has to be a legal name, followed by a list of parameters in parentheses, followed by the body of the function, the statements to be executed. The list of arguments required by a function is called a parameter list, and its elements are called parameters, or formal arguments. So we got 3 different ways of saying the same thing now. We have formal arguments, parameters, and arguments. The list of parentheses can be empty, and if we don't want to return the result, we give void, meaning nothing, as a return type. For example, void, write, sorry. Take no argument, return no value, write, sorry, to the output. The language technical aspects of functions will be examined more closely in Chapter 7. Alright, we have Section 5, Subsection 1, why bother with functions? We define a function when we want a separate computation with a name because doing so makes the computation logically separate, makes the program text clearer by naming the computation, makes it possible to use a function in more than one place in your program, and it eases testing. We'll see many examples of each of those reasons as we go along, and we will occasionally mention a reason. Note that real-world programs use thousands of functions, some even hundreds of thousands of functions. Obviously, we would never be able to write or understand such programs if their parts, for example computations, were not clearly separated and named. Also, you'll soon find that many functions are repeatedly useful, and you'll soon tire of repeating equivalent code. For example, you might be happy writing x times x and 7 times 7 and x plus 7 times x plus 7, etc., rather than square x and square 7 and square x plus 7, etc. However, that's only because square is a very simple computation. Consider square root, called square root sqrt in C++. You prefer to write sqrt x and sqr7 and sqr x plus 7, etc., rather than repeating the somewhat complicated and many lines long code for complete computing square root. Even better, you don't have to even look at the computation of square root because knowing that sqrt x gives the square root of x is sufficient. In Section 4 of Chapter 7, we address many function technicalities, but for now, we'll just give another example. If we wanted to make the loop in main in the first program really simple, we could have written void print square int v, cout v, we print v separated by a tab, and the square v in the new line, and we have int main, we iterate over, and we use the print square function. Why didn't we use the version using print square? That version is not significantly simpler than the version using square, and note that print square is rather a specialized function we could not expect to be able to use later. whereas square is an obvious candidate for other uses. Square hardly requires documentation, where print square obviously needs some explanation. The underlying reason for both is that print square performs two logically separate actions. It prints and it calculates a square. Programs are usually easier to write and to understand if each function performs a single logical action. Basically, the square version is the better design. Finally, why did we use square I rather than simply I times I in the first version of the problem? Well, one of the purposes of functions is to simplify code by separating out complicated calculations as named functions. And for the 1949 version of the program, there was no hardware that directly implemented multiply. Consequently, in 1949 version of the program, I times I was actually a fairly complicated calculation, similar to what you would do by hand using a piece of paper. Also, the writer of that original version, David Wheeler, was the inventor of the function, then called a subroutine, in modern computing. So it seemed appropriate to use it here. Try this. Implement square without using the multiplication operator. That is, do the x times x by repeated addition. Start by a variable, result at 0, and add x to it x times. Then run some version of the first program using that square. Alright, let's start a new project for this. Empty CPP project. PPP. What happened? Oh no, I hit enter on accident. New project. Empty project. PPP3 underscore try this. And this is first program. We add our main. Edit our project properties as normal. Scan sources for module dependencies to yes, language standard to C++ latest, and build ISO C++ standard library to yes. Apply, okay. This program performs the task of the world's first program. Here we do so to learn about functions. So we have an int square. We have int x as an input. And then we have an int answer equals 0. And then for int I equals 0. I is less than x. Plus I. We want answer to plus equal x. And we want to return that answer. I'll put this in curly braces. Call it a bit of a day. And we want our int main, of course, because we require it. And we want to iterate over. Int I equals 0. I is less than 100. Plus I. And we want to cout. I. Oop, we need to import std. And using the namespace std. Alright, I separated by the tab character, and then the square with I, and then the new line character. And that's about it. We want to, of course, return 0 to say that everything went well. Let's give this a go. See if this works. First try. Appears to be working. 1 1 2 4 3 9 4 16 5 25 9 9. Okay, that looks right. Did we stop? 99? Yes, we did. Okay, that worked. Move the keyboard out of the way. Let's get back to the book. Then we have function declarations. Did you notice that all the information needed to call a function was in the first line of its definition? For example, int square int x. Given that, we know enough to say int x equals square 44. We don't really need to look at the function body. In real programs, we most often don't want to look at the function body. Why would we want to look at the body of the standard library square root function? We know it calculates the square root of its arguments. Why would we want to see the body of our square function? Of course, we might just be curious. But almost all the time, we are just interested in knowing how to call a function. Seeing the definition would just be distracting. Fortunately, C++ provides a way of supplying that information separately from the complete function definition. It is called a function declaration. So we have int square accepting an int, we have declaration of a square, double square root double, we have declaration of square root. Note the terminating semicolons. A semicolon is used in a function declaration instead of the body used in the corresponding function definition. So, if you just want to use a function, you simply write, or more commonly import, or hashtag include, its declaration. The function definition can be somewhere else. We'll discuss where that elsewhere might be in section 3 of chapter 7 and section 7.1 in chapter 7 as well. Oh, well, section 7.3 through section 7, subsection 1. This distinction between declarations and definitions become essential in larger programs where we use declarations to keep most of our code out of sight to allow us to concentrate on a single part of our program at a time. This is what I was interested in. Section 6, the vector. To do just about anything of interest in a program, we need a collection of data to work on. For example, we might need a list of phone numbers, a list of members of a football team, a list of courses, a list of books to read over last year, a catalog of songs for download, a set of payment options for a car, a list of the weather forecasts for the next week, a list of the prices for a camera in different web stores, etc. The possibilities are literally endless and therefore ubiquitous in programs. We'll get to see a variety of ways of storing collections of data, a variety of containers of data. See Chapter 19 and Chapter 20. Here we will start with one of the simplest and arguably the most useful ways of storing data. A vector. We have a core concept alert marker here. A vector is simply a sequence of elements that you can access by an index. For example, here is a vector called v. We have a graphic here. We have v, and it has 6, and v's elements are aligned in a row with 0 to 5. That is, the first element has index 0, the second index 1, and so on. We refer to an element by subscripting the name of the vector with the element's index. So here the value of v of 0 is 5, the value of v of 1 is 7, and so on. Indices for a vector always start with 0 and increase by 1. This should look familiar. The standard library vector is simply the C++ standard library's version of an old and well-known idea. I have drawn the vector so as to emphasize that it knows its size. That is, a vector doesn't just store its elements, it also stores its size. We could make such a vector like this. Vector int v equals 5, 7, 9, 4, 6, and 8 separated by commas within curly braces is a vector of 6 ints. We specify the type of the elements in the initial set of elements. The element type comes after vector in the angle brackets. Here, int. Here is another example. Vector string philosopher equals Kant, Plato, Hume, and Kierkegaard, a vector of 4 strings. Naturally, a vector will only accept elements of its declared element type. So trying to put the integer 99 into the philosopher of 2 location. So replace Hume with 99. We would get an error trying to assign an int to a string, and if we tried to put Hume into the vector 2, v of 2, so trying to replace 9 by Hume, we'd get an error trying to assign a string to an int. We can also define a vector of a given size without specifying the element values. In that case, we use the n notation. N in parentheses notation, where n is the number of elements and the elements are given by a default value according to the element type. For example, vector int v of I of 6, vectors of 6 ints initialized to 0. We have vector string vs of 4, a vector of 4 strings initialized to the empty string. The string with no characters, double quotes, shown in just double quotes, not separated at all, is called the empty string. Please note that you cannot simply refer to a non-existent element of a vector. V of I, 20,000 equals 44 is a runtime error. We will discuss runtime errors and subscripting in the next chapter. Then we have a subsection 1 here, traversing a vector. A vector knows its size, so we can print the elements of a vector like this. So we have a vector of ints, v equals 5, 7, 9, 4, 6, 8. And for I equals 0, I is less than the size, v dot size. And we iterate once per loop. We increase I by 1 every loop. We print out v of I in a new line character. The call v.size gives the number of elements of the vector v called v. In general, v.size gives us the ability to access elements of a vector without accidentally referring to an element outside the vector's range. The range for a vector v is 0 colon v.size. So from 0 to v.size. That's the mathematical notation for a half-open sequence of elements. The first element of v is v sub 0, and the last is... Oh, I see. Okay, so it's a left bracket, and then the right one is a parenthesis. Mathematical notation for a half-open sequence of elements. So 0 is inclusive, but v.size is 1 minus. Okay. And the last v.size. Okay. If v.size is equal to 0, v has no elements, that is, v is the empty vector. This notion of half-open sequences is used throughout C++ and the C++ standard library. See section 2 of chapter 19 and section 7 of chapter 20. The language takes advantage of the notation of half-open sequence to provide a simple loop over all the elements of a sequence, such as the elements of a vector. For example, we have the vector of ints v equals 5, 7, 9, 4, 6, 8, separated by commas and curly braces. For x colon v, for each x in v, print out x with a new line. Huh, look at that. This is called a range for loop because the word range is often used to mean the same as sequence of elements. We read for int x colon v as for each x in v, and the meaning of the loop is exactly like the equivalent loop over the subscripts 0 colon v dot size. We use the range for loop for simple loops over all the elements of a sequence, looking at one element at a time. More complicated loops, such as looking at every third element of a vector, looking at only the second half of the vector, or comparing elements of two vectors, are usually better done using the more complicated and more general traditional for statement. We have subsection 2, growing a vector. Often we start a vector empty and grow it to its desired size as we read or compute the data we want in it. The key operation here is pushback, which adds a new element to a vector. The new element becomes the last element of the vector. For example, so we have the vector double v, starts off empty, that is, v has no elements. And we use v.pushback of 2.7. We add the element 2.7 to v at the end, or the back. And if we push v, we use v.pushback 5.6, we add an element 5.6 to the v at the end of back. Note the syntax for a call of pushback. It is a member function call. Pushback is a member function of vector and must be called using the dot notation. So a member function call is defined in the notation with object name dot member function name and then in parentheses the argument list. The size of a vector can be obtained by a call to another vector's member function, size. Initially, v.size was 0, and after the second call of pushback, v.size has become 2. If you have programmed before, you will note that a vector is similar to an array in C and to other languages. However, you need not specify the size length of a vector in advance. You can add as many elements as you like. As we go along, you'll find that C++ standard vector has other useful properties. And we have a subsection 3 on a numeric example. Let's look at a more realistic example. Often we have a series of values that we want to read into our program so that we can do something with them. The something could be producing a graph of values, calculating the mean and median, finding the largest element, sorting them, combining them with other data, searching for interesting values, comparing them to other data, etc. There is no limit to the range of computations we might perform on data. But first, we need to get it into our computer's memory. Here is the basic technique for getting an unknown, possibly large amount of data into a computer. As a concrete example, we choose to read in floating point numbers representing temperatures. So we have a small program here where we start with a vector, an empty vector of temps, storing doubles, and then for double temp, we grab in so for a double, so I guess I'll be doing this forever? Yeah, I guess we're doing this forever. For double temp, I think this is as long as we get something. Okay. So we declare a double temp, which will initialize as 0, and then for each loop that we do, we check to see the value of cin is true. Cin, we get from cin to temp, and as long as we're getting something, this is true. And we continually loop and get new temp values, and each time we loop, we push back into temps the temp that we got. So what goes on here? First, we declare a vector to hold the data. Vector double temperatures. This is where the input we expect is mentioned. We read and store doubles. Next come the actual read loop. We define a variable temp of type double to read into. The cin get from operator temp reads a double, and that double is pushed into the vector placed at the back. We have seen those individual operations before. What's new here is that we use the input operation cin input get from operator temp as the condition for our for statement. Basically, cin get from temp is true if the value was read correctly and false if otherwise. So that for statement will read all the doubles we give it and stop when we give it anything else. For example, if you typed 1.2, 3.4, 5.6, 7.9, 9.0, and then the vertical bar, then temps would get the 5 elements, 1.2, 3.4, 5.6, 7.8, 9.0 in that order, for example. We use the character vertical bar to terminate the input. Anything that isn't a double can be used. In section 4 of chapter 9, we discuss how to terminate input and how to deal with errors in input. To limit the scope of our input variable temp to the loop, we use a for statement rather than a while statement. As usual, a for loop shows what is going on up front, so that the code is easier to understand and accidental errors are harder to get. Once we get data into a vector, we can easily manipulate it. As an example, let's calculate the mean and median temperatures. So we have int main, compute mean and median temperatures. So we have a vector of doubles for named temps, and we have that iterator of getting temps, as we saw before. We compute the mean temperature by initializing a sum to 0, and then we iterate for every temp in temps. So double x colon temps. So for every temperature in temps, we add that to our sum. We add equals that to our sum. And then after that, we print out the average temperature is the sum divided by how many temperatures we had recorded. And then we compute the median temperature. So we use the ranges sort function on temps. So we sort the temps that we got. And then the cout median temperature is the value in temps, which is in the middle. So the temps.size divided by 2, wherever that ends up us at, in the array, grabbing from temps, we grab that value. Since it's sorted and it's in the middle, that means it's the median temp. And we print that. We calculate the average, the mean, by simply adding all of the elements into sum and then dividing the sum by the number of elements, that is, temps.size. So we compute the average temperature down here. This is what we just read above. Note how the plus equals operator comes in handy. To calculate a median, a value chosen so that half of the values are lower and half of the values are higher, we need to sort the elements. For that, we use a variant of the standard library sort algorithm, sort. In which case, we use ranges, : sort, temps. We will explain the standard library algorithms much later in chapter 21. Once the temperatures are sorted, it's easy to find the median. We just pick the middle element, the one with the index temps.size divided by 2. If you feel like being picky, and if you do, you are starting to think like a programmer, you could observe that the value we found may not be the median according to the definition we offered above. Exercise 3 at the end of this chapter is designated to solve that problem. We deliberately left a potential worse problem in that code. Did you spot it? What happens if we don't enter any temperature values? In that case, all is well until we try to output the median temperature. Then we try to read temps.size divided by 2, but temps.size is 0, so there is no elements to read. Fortunately, if you use an implementation of vector that does range checking, the error is caught and reported. If you use our PPP support, that's what happens. Forgetting the case of no elements is a common problem when iterating. Always consider that possibility. And we have subsection 4 of vectors. We have a text example. We didn't present the temperature example because we're particularly interested in temperatures. Many people, such as metrologists, ergonomists, oceanographers, are very interested in temperature data and values based on it, such as means and medians. However, we are not. For a programmer's point of view, what's interesting about this example is its generality. The vector and simple operations on it can be used in a huge range of applications. It is fair to say whatever you are interested in, if you need to analyze data, you'll use vector, or a similar data structure. See Chapter 15. As an example, let's build a simple dictionary. The simple dictionary, a list of sorted words. So we have a vector of strings called words, and we get words from this loop, this for loop. So as long as we're getting valid strings, we will exit. As long as we're getting valid strings, we're going to put them in the words, and then we're going to print out how many words we have, and then we're going to use the ranges : sort function to sort our words, our vector string of words, and then we're going to print. We're going to iterate over our words vector, and what is this? As long as the word that we're using is either we're starting at the beginning, or the word just before the one we're checking is not equal to the word that we are checking, we'll print it out. So we're not going to print duplicate words. This little line right here is helping us do that. If we feed some words to this program, it will write them out in order without repeating a word. For example, given a man, a plan, a canal, Panama, it will write a canal, man, Panama, plan. That sounds really fun to say. How do we stop reading string input? In other words, how do we terminate the input loop? That's interesting. Yeah, how do we get out of that? I don't know how to do that. Oh, the Control Z. Okay, we use that. When we read numbers, we just give some input character that wasn't a number. We cannot do that here because every ordinary character can be read into a string. Fortunately, there are characters that are not ordinary. As mentioned in subsection 1 of section 5 of chapter 2, Control plus Z, or Control Z, terminates an input stream under Windows, and Control D does that under Linux. Most of this program is remarkably similar to what we did for the temperatures. In fact, we wrote the dictionary program by cutting and pasting from the temperature program. The only thing that's new is the test. With int I equals 0, or words, or the word before is not equal to the word that we're checking now. If you deleted that test, the output would be a canal, man, Panama, plan. We didn't like the repetition, so we eliminated it using that test. What does the test do? It looks to see if the previous word we printed is different from the one we are about to print. And if so, we print that word. Otherwise, we do not. Obviously, we can't talk about the previous word when we're about to print the first word. So when I equals 0. So we first test for that and combine those two tests using the OR operator. Note that we can compare strings. We use the not equals. Here, equals, double equals, less than, equal to, greater than, equal to, also work for strings. The less than, greater than, etc. operators are use the usual lexicographical ordering, so ape comes before apple and chimpanzee. Try this. Write a program that bleeps out words that you don't like. That is, you read in words from cin and print them out again on cout. If a word is among a few you have defined, you write bleep instead of that word. Start with one disliked word, such as string disliked equals broccoli. When that works, add a few more. Now let's try this. We're almost done. Let's create a new project for this. An empty C++ project. Grab our keyboard. PPP3. Try this. Bleeper. Source files, we add a main CPP, go here, do project properties, and we want to go C to C++, general, scan sources for module dependencies to yes, our language standard, we want to change that to latest, and the build ISO C++ standard library to yes, we apply these changes, we give this program a short description, this program echoes repeated request for echoes input in a loop, replacing bad words with bleep. Alright, we want to import std. We use the namespace std main. We want to return 0. Return 0. Alright, so we want to vector strings. Words. Wait, we don't want that. Do we? Oh, we do want a vector. String. Bad words. Broccoli. Let's just say bad. Bad is very bad. Horrendous is a bad word as well. Murder. That's a bad word. Heck. That's a super bad word. Alright. I think there's enough bad words for us. And then we have a string temp. And then for actually, we could just do it like this. how do we know if temp is one of the bad words? Okay, I know how. For string s in bad words, or BW in bad words, if temp is equal to BW, we want to print out bleep and if we end up bleeping, I was going to use the break. How can we break out of both? Now we can a bull broken. In bad word, or is bad word equals false. And if we find it to be a bad word, we're going to make it true. And if we want to break here. And if it is a bad word, we want to print the bleep. Else, we want to just print out temp. Okay. Not just temp, we want to print out a new line. Let's give this a go. Ah, my bones! Ow! Oh, we never prompted for input. Please enter some words. Please be polite or we'll bleep ya. Good. Happy. Let's try bad. Bleep. Let's try... Oh, well, it printed out bleep, but not with the new line character. Bad. Horrendous. Murder. Flower. Ocean. Yeesh. Alright, that works, I guess. Write a program that bleeps out words that you don't like. That is, you read in words using cin and print them out again on cout. If the word is among a few you have defined, you write out bleep instead of that word. Start with one disliked word, such as that, and add a few more. Well, that works. It bleeps out words that you don't like. Okay, it doesn't... this is like echoing. I don't want to echo. Yeah, no echo. We have a vector string of words, and we want our words dot pushback bleep. We want to just push back the word we found. And then string s words we want to print them out. Each on a new line. Okie dokie dokie day, okie dokie day, okie dokie day. Good, happy, bad, bad. So Z. Good, happy, bleep, bleep. Woohoo! Works on the first try. Yippee. Let's open it back up. Section 7, Language Features. The temperature and dictionary programs use most of the fundamental language features we presented in this chapter. Iteration, the for statement, and the while statement. Selection, the if statement, simple arithmetic, the plus plus, the it could be preemptive or post-emptive. The incremental operator, the plus equals operator? I forgot what that's called already. Comparisons and logical... I know exactly how it works, but I don't know its name anymore. Comparisons and logical operators like the equals, the not equals, or the or operators. Variables and functions, the main, sort, and size. In addition, we use the standard library functions such as vector or container of elements, the cout, the output stream, sort, and algorithm. If you count, you'll find we've actually achieved quite a lot of rather few features. That's the ideal. Each programming language feature exists to express a fundamental idea, and we can combine them in a huge, really infinite number of ways to write useful programs. This is a key notion. A computer is not a gadget with a fixed function. Instead, it is a machine that we can program to do any computation we can think of. And given that we can attach computers to gadgets that interact with the world outside the computer, we can, in principle, get it to do anything. That is a super core concept. Thank God. We're done, and we've hit the drills. Alright. I'll end it off here. That was Chapter 3's reading and Let's Tries in Programming Principles and Practice using C++ 3rd Edition. I am going to take a well-deserved break. Thank you for watching. I'll be back with a new video sometime during the week on the drills. Thank you for watching and bearing with me as I struggle to get Unicode working with the console output stream, which seems to not support it unless you do a lot of weird environmental changes. Thank you.